Hello everyone, welcome to video lecture of ME312 Metrology and Instrumentation. I am Manu Joseph, Assistant Professor, Department of Mechanical Engineering, Rajagiri School of Engineering and Technology. Module 5, Lecture 2. In this lecture, we will be discussing about the performance characteristics of measuring devices. When we want to use an instrument for a particular application, we should know its performance. Then only we can select the right tool or right instrument, and also we can compare the instrument. So the performance characteristic is the functional characteristic of an instrument for a particular application. We have two types of performance characteristics. One is called static characteristics, another one is called dynamic characteristic. Static characteristic and dynamic characteristic. The static characteristic is independent, the characteristic which is independent of time. That is, the static characteristic refer to the characteristic of the system when the input is either held constant or varying very slowly, or that should not vary with time. That is characteristic independent of time. These are the different static characteristics: accuracy, precision, range, sensitivity, reproducibility, drift, resolution, hysteresis, threshold, linearity, bias, and dead zone. So we will discuss these static characteristics in detail in this lecture. So we start with accuracy. Accuracy is how close the measured value to the true value, or it indicates the closeness of measured value with the actual or true value. It is actually a manifestation of error in measurement. And it is also expressed as a percentage of true value. That's about the accuracy. Then precision. An instrument is said to be precise when we take repeated measurement using this instrument for same quantity. We should get results, output, which are close to each other. So the precision is nothing but degree or agreement between different reading. Precision indicates repeatability and reproducibility of the instrument. If an instrument is used to measure the same input but different instant, the successive measurement may vary randomly. A precision instrument indicates that successive readings should be very close. In other words, the standard deviation sigma E of this set of measurement would be very small. Sigma E should be very small, then the instrument is said to be precise. That's about the precision and accuracy. Then range or span. Range defines the maximum and minimum value of an input or the output for which instrument is recommended to use. Or the range or region between the limit within which the instrument is designed to operate for. So the region between the limit within which instrument is designed to operate for. For example, a pressure gauge, its minimum value is 0 and maximum value is 50 bar, 0 bar and 50 bar. So its range is values in between 0 and 50. Then the next characteristic is sensitivity. It can be defined as a ratio of incremental output and the incremental input, or it can be defined as, for little more clearly, is the ratio of magnitude of change in output signal to the magnitude of change in input signal. Change in output signal to change in input signal. While defining sensitivity, we assume that input-output characteristic or relation of the instrument is approximately linear. Linear means it can be expressed in a straight line. The relationship can be expressed in a straight line. Okay. Again, for an instrument, sensitivity may vary with the temperature or other external factors. This is known as sensitivity drift. This variation of the temperature, so variation of sensitivity with temperature or some other factor is called sensitivity drift. To avoid that, we keep the instrument, sensitive instrument or sophisticated instrument, at controlled temperature, or will give suitable inbuilt temperature compensation scheme are provided inside the instrument to compensate the sensitivity. So this is representation of sensitivity. We have output and input. This output-input relation is a linear relationship. It can be expressed y is equal to mx plus c, mx plus c, y is equal to mx plus c, or y is equal to mx. So this is q out, the output. This is q in, input. So sensitivity is infinitesimally change in output for a change in input. So change in output by change in input. So delta q0 by delta qi, that is sensitivity. Okay, so the magnitude of change in output to ratio of magnitude of change in output to change in input is called sensitivity. So another characteristic is reproducibility. So it can be defined as degree of closeness with which a given value may be repeatedly measured with a different instrument, different location by different observer. Please note, a different instrument with using different instrument at different location by a different instrument, we measure the same physical quantity. If the degree of closeness, if they are close to each other, then we can say it's reproducible. Reproducibility is high. Reproducibility is high. Okay, it is the reproducibility is specified for a period of time. Okay, the people involved in fabrication purpose. People involved in fabrication purpose. What they do? They take the measurement from the site, and they reproduce the same dimension on their work area. So that should be reproduced, that should be matching, then only it become, this component they produce can be utilized for specific application. So suppose we are ordering a component, we are ordering our design, giving our design, that is, suppose it's a disc with certain slots, certain holes, or certain dimensions. The manufacturer manufacture that component with their, and check that dimensions with their instruments. So when we take the dimensions again, those physical quantity again from our place, they should be matching. That is reproducibility. And reproducibility is specified for a period of time. The perfect reproducibility signifies that the given reading that are taken for an input do not vary with the time. Should not vary with the time. That is, then it's perfect reproducibility. Next is an important term, that is drift. Drift. The drift is defined as gradual shift in the indication over a period of time wherein input variable does not change. The drift is defined as a gradual shift in the indication over a period of time wherein the input variable does not change. Or it can also be defined as undesirable or undesired departure of the instrument output over a period of time. So over a period of time, instrument output is varying. That is drift. And it may cause because of different factors like environmental factors like stray electric field, stray magnetic field, thermal EMF, change in temperature, mechanical vibration, etc. These factors cause the drift. These are the different types of drift. We have zero drift, span drift or sensitivity drift, and zonal drift. We will study in detail about this drift. The first one is zero drift. The instrument is showing a different value or giving an output when the input is zero. It's not coinciding with, the needle is not coinciding with the zero when the input is zero. So input is zero. You're giving some value, say 5 volt, when the input is zero. That is zero drift. So if whole calibration gradually shift due to slippage or permanent set or due to undue warming up of electronic tube circuit, zero drift set in. Due to wear and tear also result. But in zero drift, the specialty is this drift does not affect the input-output relationship. Here in this graph, we can see plot. We can see input-output. This here we have a linear relationship. This is normal characteristic without any drift. We have for zero input, zero output. But this is characteristics with zero drift. When we have zero input, we have a particular value of output, say 5 volt. So, but we can see when we look in the slope of this curve and slope of this curve, that will be same. That means there is no change in the input output relationship due to this zero drift. Another type of drift is called span drift or sensitivity drift. Here there is a proportional change in the indication all along the upward scale. So all along the scale there is a proportional change. That means the input-output relation, in input-output relation there is a change. So when we look into this plot, input-output, we have linear relationship, but when we look in the slope of both normal characteristics and span drift, there is a difference. There is a change in the input-output relationship throughout the reading, the span drift. So the reason for this, the tip of the primary sensing element, the main sensing element, has changed or has damaged. That is the reason for, and it's giving a faulty reading. So that is span drift. And thus next, the last one is zonal drift. In this case, the drift occur only a portion of the span of the instrument. Only a portion of the instrument drift occur. Example is that is called zonal drift. Drift occur in this portion. So that's about the drift. This drift can be defined as undesirable departure of the instrument output over a period of time. We have 3: zonal drift, span drift, and zero drift. The next term is resolution. Resolution indicate minimum change in the input variable. Minimum change in the input variable that is detectable. So detectable means the minimum change in the input variable, there should be some output. If the input is slowly increased from some arbitrary input value, if we are increasing the input from an arbitrary value, it will again be found that output does not change at all until certain increment is exceeded. So up to certain level, there should not be any change in the variation, the indicator output. There is no output variation with change in the input. And this increment is called resolution. That is the increment when the output indicates a change. That is called resolution. So we can see delta I. So for delta I change in the till delta I change in the input value, the output remain same. When it reaches the delta I change, there is a output change. Before that, there is no change in the output. Okay, the output is, say, this is 5 volt, this is 5 volt. So if we indicate the voltage change, it does not show any indication in the instrument. So it is always expressed as percentage. Resolution is equal to delta I by delta I max minus I minimum into 100. Delta I max, so this is I max and I minimum by 100. That is resolution. Now threshold. The threshold is smallest measurable input. Is the smallest measurable input below which no output change can be identified. That is, when we start reading from zero, the point up to which there is no variation, there is no output, that's called threshold. So it can be defined as, if the instrument input is very slowly or very gradually increase from zero, there will be a minimum value required to give a detectable output change. That minimum value is called threshold. That is, if the instrument input is varied gradually from zero, that's not that point, zero, there will be a minimum value required to give a detectable output change. That minimum value is called threshold. And while specifying the threshold, the manufacturer gives first detectable output change. When specifying threshold means it's giving the first detectable output change. Okay, now hysteresis. So hysteresis is a phenomenon which depicts different output effect while loading and unloading. While loading and unloading, the output result is different. Okay, that is hysteresis output. That means output depends upon the direction of loading. We increase loading from 0 to maximum value for a particular input, there is a output. So when we are reducing the load from that maximum value to 0 for the same particular input, particular load, if you take the output value, that will be different. That is due to hysteresis. So just like that is similar to magnetic hysteresis. So similar to magnetic hysteresis, there is a hysteresis in mechanical or instrument also. Hysteresis, and this hysteresis take place due to the fact that all energy put into the stress part when loading, is not recoverable while unloading. It's not recovered. So that will be remain as some residue in the instrument. Because of that residue, the value will be different, reading will be different. Example, a flow meter. If we gradually open the valve from 0 to maximum value, we take the reading of the flow at a particular valve opening, we get some value, and then we are reducing the flow rate by closing the valve from maximum to 0. So same valve opening, if we take the reading, the discharge reading will be different. That is due to hysteresis. When input of an instrument is varied from 0 to full scale, and then if the input is decreased from full scale to 0, the output varies. That means output at a particular input while increasing and decreasing varies. Decreasing and increasing, the output of a particular input will be different, and it can be due to this hysteresis may be due to internal friction or hysteresis damping. Okay, So that is hysteresis. Hysteresis nothing but the output of an instrument depend upon direction of loading. So here we can see this is the input output relationship, input 0, output 0. We are increasing the input, we are increasing the quantity or flow rate quantity. Up to certain limit there is no output. So this is the threshold, the minimum value up to which there is a noticeable change in the output, or there is a noticeable output. So after threshold it's keep on increasing. This is the increasing range. So here we reach the maximum output or maximum output. So when we decrease, here we can see this is the decreasing input is decreasing. So here we can see, so both are following a different path. It's not like this, coming like this and retaining the same path. So this phenomenon is hysteresis. During hysteresis, if we take a particular input value Qi, we have two output. This is one output, this is another output, these two output. So this is hysteresis, and this is threshold, and the region where there is no output when there is input is called dead band. This is the dead band, that is dead band. So that is about hysteresis. Its output depends upon direction of loading, that is hysteresis. So next is bias. The constant error which exists over full range of measurement of an instrument is called bias. There is a constant error that exists in the full range of instrument, bias. It can be eliminated by calibration. Zero error that will be exist throughout the reading. So that is an example for bias which can be removed by a proper calibration. Then we have linearity. So linearity indicates or it can be defined as ability to reproduce the input characteristic symmetrically and linearly. That is, input output relation should be linear. In ideal case, the input output relationship is a straight line, that will be y, the output is equal to y is equal to mx, or y is equal to mx plus c. So that's the equation for straight line. Input output is a straight line for ideal case. For many of the instrument that deviate from the ideal behavior, it's not an error actually. It's not an error. That means won't affect the accuracy. So here we can see this is idealized straight line. So linear ideal linearity. Here we can see there is a curve. It's not linear. So this non-linearity, the deviation from the linear behavior, is known as non-linearity. It is defined as, or it is a difference between the maximum output and maximum output in this curve, the actual output and the output in linear or idealized instrument. So if this is XA and this is XB, XA minus XB will give the linearity, the maximum deviation from the linear behavior of the instrument. That is called a non-linearity. Okay, this gap is the maximum deviation from the linear behavior, that is non-linearity. Then we have a zone called dead zone, as I said before, the largest change in input quantity for which there is no output. The input that is applied to instrument may not be sufficient to overcome the friction. So it will only respond when it overcome the frictional force. That is called dead zone. So that is about the static characteristic of an instrument, and we found that static characteristic is the characteristic which is independent of time. When the instrument reading is independent of the time, we can apply the static characteristic. We found there are many static characteristics like accuracy, precision, linearity, hysteresis, repeatability, reproducibility, bias, range, etc. Now we are moving to dynamic characteristic. The dynamic characteristic, so that is the characteristic of an instrument. That's the characteristic of an instrument when the output or input depend upon time. So dynamic characteristic refers to performance of an instrument when input variable is changing rapidly with the time. Input is variable is changing rapidly with time. The instrument rarely responds to instantaneous change in the measured variable. Their response is slow or sluggish due to mass, thermal capacitance, electrical capacitance, inductance, etc. The behavior of such system, where input varies from instant to instant, the output also varies from instant to instant, is called dynamic response of the instrument. I repeat, behavior of system where input varies from instant to instant and output also varies from instant to instant is called dynamic response of a system. Input and output depends upon time. Then the response is called dynamic response. So we have this time varying input. We have two types: transient input and steady state periodic. One is transient, but other one is steady state periodic. So, and also the input, variation in the input that are used practically to achieve dynamic behavior are many types. One is step input, that is input subject to finite and instantaneous change. Like there is no continuous, input is not varying continuously, just like 0 and 1, 0 and 1. So it's having a finite value, not continuous value. It's called step input. So example, closing a switch. We have two conditions, open or close. It's time varying. At one instant of time is open, other instant is closed. So 0 and 1 is there. Then ramp input, the input linearly changes with the time. Linearly changes with respect to time. It's a straight line relationship with the input and time. Then parabolic input, that is the input varies to the square of the time. Y is equal to x square. This represents a constant acceleration. Then we have sinusoidal input, that is input is sinusoidal. Input change in accordance with the sinusoidal function of a constant amplitude. The input increases from 0 to maximum value, then decreases, then negative value, then increases, 0, increases to maximum positive value. This is sinusoidal input. There is a different input for the study of dynamic behavior. Now, dynamic characteristic of a measuring system. We have 4 dynamic characteristics. We are going to study about 4 dynamic characteristics. One is speed of response. How fast? Speed of response is represent how fast an instrument respond to a change in a quantity. Rapid, or it can be defined as rapidity with which an instrument responds to a change in the value of the quantity being measured. Respond to change in the quantity being measured. It is so how active or fast the system is. How active or fast the system, that is speed of response. Then another important dynamic characteristic is fidelity. It is defined as degree to which a measuring system is capable of faithfully reproducing the change in the input. The degree to which a measuring system is capable of faithfully reproducing the change of input without a dynamic error. How faithfully it reproduces the change in input. Or degree of closeness, it can be fidelity, can be described degree of closeness with which a system indicate or record the signal which is imposed on it, or degree of closeness with which the system indicate or record the signal which is imposed on it. That is fidelity. So it refers to ability of the system to reproduce the output in the same form of the input. Poor fidelity indicates the non-linearity. That means input and output are not linear. Whatever the change, that would be made in the output. Faithfully, that should be indicated in the output. Then lag. Every system requires its own time to respond to the change in the input. This is called lag. For every output, there is a time for that instrument to respond to the change. That is called lag. It can be defined retardation or delay in the response of system to change in the input. Suppose the lag. And we have two types of lag: retardation lag and time delay. As soon as there is a change in the measured quantity, the measuring system begins to respond. That's retardation lag. And the time delay, that the response of the measuring system starts after a dead time. For a dead time, the instrument will not show the output. Response of the system starts after a dead time. Once input is applied, this causes dynamic error. It takes some time to give a response. Then dynamic error is the difference between true value of the quantity, that is to be measured, and changing with the time, that is changing to be time, and the measured value. The difference between true value of the quantity that is to be measured, which is changing with the time, that's dynamic quantity. Quantity's input is dynamically, so the value is changing dynamically. The true value minus the measured value when this input is changing, and then that is called dynamic error. One condition here, the static error is assumed to be 0. So once again, dynamic error can be defined as difference between the true value of the quantity that is to be measured changing with the time and the measured value if no static error is assumed. So that's about different dynamic characteristics. Dynamic characteristics are the characteristic of the instrument when the input or output relationship output varying with respect to time. We have different type of dynamic characteristic: speed of response, fidelity, lag, and dynamic error. Okay, so in today's lecture, we discussed about performance characteristic of a measuring instrument, and we found that there are two types of performance characteristics. One is static characteristic and dynamic characteristic. These characteristics should be known while selecting an instrument, because it expresses or it represents the performance of an instrument for a particular function. So we study different static characteristic and dynamic characteristics. That's about today's lecture. Thank you for listening.